Hitting Enter on a keyboard or clicking a hyperlink initiates a chain reaction across global infrastructure. It starts an unseen process spanning multiple networks. The speed of a modern web browser creates an illusion of simplicity. Behind a sub-second load time, thousands of servers and miles of fiber optic cable execute a sequence of operations, masking the web's underlying complexity. To understand how Internet architecture functions, we must trace the exact life cycle of a web page request. We will follow the data from the initial string parsing in the address bar to the final pixel rendered on the screen. This timeline maps out the network protocols and computational steps necessary to connect the client to the server. The lifecycle consists of two phases: global network routing to locate data, followed by localized data transformation to display it. Analyzing this precise architectural sequence is a core competency for the performance engineering teams at Royal Research. Effective performance optimization requires a complete map of this sequence, as delays at any individual stage contribute to the total latency experienced by the user. The first step occurs within the browser, which dissects the URL string to isolate three elements: the protocol, the domain name, and the specific file path. String parsing alone is insufficient for routing. Computers communicate using numerical IP addresses, and they cannot interpret human-readable domain strings without a translation layer. The domain name system translates domains into IP addresses. It first checks the local cache. If empty, it escalates to the ISP. If needed, it queries the global hierarchy until the authoritative server resolves the query, returning the IP address back to the client. The operating system caches this IP address locally. This ensures that subsequent requests to the same domain can bypass this lookup process. DNS resolution is the first potential bottleneck. Without a mapped IP address, communication with the web server cannot begin. Now, with the target IP address identified, the browser begins establishing a direct communication line with the server. The browser initiates a transmission control protocol connection, typically over port 443. TCP is a standard that ensures data packets are delivered reliably and in the correct order. This illustrates the TLS handshake. Transport Layer Security, or TLS, is a cryptographic protocol that verifies the server's identity and sets up encrypted communication. This handshake ensures that all data transferred between the client and server is encrypted and protected from outside interception. Inside this secure tunnel, the browser sends an HTTP request. This includes specific methods like GET, along with headers that tell the server what type of content the browser can process. The server receives the request, executes its internal logic, and queries its databases to retrieve or assemble the requested information. The server then transmits an HTTP response. This includes a status code, such as 200 OK, followed by the raw payload of HTML, CSS, and JavaScript files. The arrival of the HTTP response concludes the network journey. At this point, the task of generating the page moves to the local computer's rendering engine. The rendering engine must now transform raw text files into a visual interface. The engine begins the parsing phase, reading the HTML document to understand the page's structure. This diagram shows the construction of the Document Object Model, or DOM. The DOM is a tree-like representation of every element on the page. Concurrently, the browser parses CSS to build the CSS containing the styling rules for those elements. However, JavaScript can interrupt this entire process. Since scripts can modify both the DOM and CSSO, the browser often stops parsing the page to execute JavaScript as it is discovered. Once parsing is complete, the DOM and CSSOM are combined into a third structure, the render tree. The render tree only includes elements that will be visible on the screen, excluding anything designated as hidden by the style rules. In the layout phase, the browser uses the render tree to calculate exact dimensions and position of every element relative to the user's screen size. During the painting phase, the engine fills in actual colors, text, and images. Finally, the browser performs compositing. It organizes different elements into layers and flattens them to create the final image shown on the monitor. The rendering phase is a strictly sequential process. A delay in parsing the HTML or CSS tree can prevent the entire page from appearing. This complete lifecycle timeline illustrates the interdependent sequence at the core of every web request, linking global network protocols with local processing. A core principle at Royal Research is that high-performance architecture depends on shortening the total duration of this timeline. The multi-step DNS lookup is a primary area where latency can accumulate before a single bit of web page data is sent. Engineering solutions included minimizing unique domain requests and using caching to remove the lookup phase from the critical path. The HTTP phase is often slowed by the physical distance data must travel between the user and the server. Content delivery networks, or CDNs, store data at the network edge. This reduces the time required for data to travel to the client. Within the local machine, oversized assets and synchronous JavaScript can block the rendering engine and prevent the page from displaying. Compressing media and deferring non-essential scripts allows the browser to build the render tree without interruption. Optimizing these individual stages results in a more efficient, responsive timeline. Understanding and controlling each microsecond of this lifecycle is what separates a standard application from highly optimized web infrastructure.